All right, we are going to use the HTG form to do a claim about a mean where sigma is known. You wish to test the following claim at a significance level of 0.02. So they've given us this set of hypotheses here, and they're telling us that the claim is in the alternative hypothesis. And we believe the population is normally distributed, and you know the standard deviation from the population is 6.5. You obtain a sample mean M of 69, that could be written as X bar, for a sample of size n equals 41. So now let's go ahead and organize that information. We have the sample mean for a sample of size n equals 41, a sample mean X bar is 69.4. Zoomed in a little bit here and make it easier for you to see. Your sigma, the population standard deviation, is 6.5. Okay, so we'll use that as we conduct our test. And the claim is that the population mean is greater, what is it? Not equal to 68.2, or you could say different from 68.2. And normally there's context, like it would tell you what kind of information it was, and the claim would be, something that would make sense for the situation, like test the claim that IQ scores are greater than 100 or something like that. And so if you have context, you should put that in your claim. But we don't have that, so we'll just use the symbols, and we are testing a mean, so the population parameter would be the Greek letter mu, and the relation symbol here is not equal, so we'll use exclamation point and the equal sign. The claimed value of 68.2, we're testing to see if it's not that, but we're going to do it under the assumption that the null hypothesis is true, so that we use the equal sign there. Oops. And then again, mu for the alternative hypothesis, and since there's no equality in the claim, it does end up being the alternative hypothesis. And that makes this a two-tailed test because we always look at the sign in our alternative hypothesis. And we have a z-test here because our sample standard deviation is not all we have to work at this time. A lot of problems you have only the sample standard deviation, you would do a t-test. But here we have the population standard deviation, so we can use the z-scores. Now we're doing a two-tailed test with a level of significance given as 0.02. And since it's two-tailed, that means the left area will be half of that amount. So let's go ahead and divide that in half. And then we can find the boundary for the critical region. We'll have two boundaries, and they're going to both be z-scores. We'll have a plus and a minus. And we'll use norm dot inverse with the left area, mean of 0, standard deviation of 1. And let's make that positive. So we'll use the absolute value symbol. So we have two critical values. We have plus and minus 2.326. Now the test statistic will be calculated by taking our sample statistic X bar and turning it into a z-score. So just like our critical value is a z-score, our test statistic will be a z-score. The sample mean, 69.4, is less than the claimed mean, so this will be a negative z-score. And to convert a sample mean into a z-score, we use the z-score formula where you take your sample mean, x bar, you subtract from it the claimed or assumed population mean, and then you take that quantity and divide it by the standard error. The standard error can be calculated separately, or you can do it right there. I like to do it separately because then I don't have to worry so much about all the parentheses that I might need. So I'm going to do the standard error as sigma divided by the square root of n. This is where we're using the central limit theorem here, and n is 41. So now, when I do my z-score with x bar minus the claimed mean and divided by the standard error, I get my test statistic of 1.182. And does that make sense? Because I had a sample mean that was greater than my population mean. I'm not sure what I said before, but it is greater, so it should be positive. I said negative. I don't know why. I don't know why at the time I said that, but let's fix it because it should be positive since it is greater than the claimed mean. Okay, and so that looks like it might be right. Let's go ahead and test it out. We'll submit that. Okay, so far so good. Now the p-value is the probability that is attached to that test statistic. So we can find the area in the right tail because it's positive. It would be the area to the right. Or we can use the negative version of the test statistic to find the area in the left. And either way, that would be half of our p-value. Just like our alpha is split up into two tails, our p-value can be thought of in that way as well. So I'm going to use norm dot distribution to find an area, and I'm going to use negative test statistic so that it'll give me the area to the left of the negative twin, and mean of 0, standard deviation of 1, as always for z-scores, and 1 for cumulative. And then my total p-value will be double that amount. So we only multiply this by 2 when we have a two-tailed test. Otherwise, you would just find one area. Okay, so the p-value here, let's compare it to the significance level. So we have a p-value of 0.237 and a significance level of 0.02. So the p-value is greater than alpha, which means we will fail to reject the null hypothesis. Okay, we could have also come to that decision by looking at the test statistic. The test statistic 1.182 compared with the critical value, which one is more extreme? In other words, which one is farther away from 0? The z-score for our critical region is more extreme. So I would say our test statistic is just not extreme enough for us to reject the null hypothesis. We have to make it to the critical value or beyond into the tail so that your test statistic would fall in the rejection region, and that's not happening here. So let's look at the sketch. That's the whole point of doing these values, because it gives us an overview of the test. So our critical value is on both sides of the picture here. So we have a positive critical value, z equals 2.33-ish, with an area of alpha half to the right, and that is 0.01. And then the twin value over here, I should have shown this better. That z-score should be farther to the right, 2 ticks over. So it's actually closer to the edge, but I don't know. It's going to be too tiny then for me to really be able to illustrate. So I'm going to leave it where it is. Negative critical value is negative 2.33. And the area in the left tail is also alpha half, which is 0.01. And the test statistic of positive, was it positive 1.182, falls outside of the rejection region. So we will fail to reject. Also, our p-value on this side is half, and that was 0.119 when you round it. That's the half right area. And so if you double that, you get the total area. And you don't have to show both sides because there really is only one test statistic, but you can think of it as if it were on both sides. So I think we're just about finished with this, right? We just have to draw a conclusion about the original claim. The original claim was that the population mean was not equal to 68.2. We failed to reject the null hypothesis, so therefore we don't have enough evidence to support the alternative which contains the claim. So we will say there is not sufficient evidence to support the claim.